The hands of a clock still move across its face, but inside the gears are silent, frozen, broken, motion without cause, a rhythm without heartbeat. What if the universe itself is such a clock? What if its final gear has already stopped turning, and yet to those inside, the illusion of motion continues? Humanity experiences time as a river, a steady current carrying the present into the unknown. Seconds become minutes, days unfold into years, and memory builds the scaffolding of identity. But physics tells another story. Einstein revealed that time is not universal, not absolute, but a pliable thread woven into the fabric of space-time. To a traveler rushing near light speed, moments stretch. To an observer beside a black hole, moments collapse. Time is not fixed. It bends, slows, fractures, and entropy, the cosmic accountant of disorder, insists that the arrow of time must march forward. Stars ignite, burn, and die. Heat disperses, structures dissolve, memory accumulates. Yet even this law whispers a darker possibility, that the direction of time, the sensation of its flow, may not be fundamental at all, but an emergent story told by matter drifting toward decay. Some theories suggest that all of history already exists, the Big Bang, the present, and the end, locked together in a silent monument of space-time, a frozen cathedral in which every moment is eternal and where movement is only the ghostly illusion of perspective. So the question lingers in the silence: is time truly flowing, or are we only watching the fading shadow of a clock that stopped long ago? These are the questions we now seek to answer. Prepare yourself. We begin. For most of human history, time was not a scientific concept. It was a rhythm, the beating of a heart, the waxing of the moon, the slow return of seasons. To the ancients, time was cyclical, an eternal wheel repeating itself. In Mesopotamia, the great calendars were carved from the heavens, mapping the motions of planets and stars across the firmament. In Egypt, the flooding of the Nile set the cadence of civilization. In Mesoamerica, priests counted days through interlocking calendars of ritual and harvest, seeing not a line, but a circle that returned endlessly. Time was a divine pulse, breathed into the cosmos by gods and spirits, measured by shadows and stones. The past, present, and future did not stand apart, but folded together into a cycle of return, birth, death, and rebirth, endlessly repeating. But then, in Europe of the 17th century, a new vision emerged. The philosopher and mathematician Isaac Newton looked at the heavens not as myths, but as mechanisms. The planets for him were not symbols, but projectiles obeying universal law. And time, in Newton's view, was not a circle, but a stage, infinite, absolute, invisible. Newton wrote that time flows equably without relation to anything external. It was a backdrop, unaffected by the motions within it. Seconds ticked forward identically in London as in the depths of space. It was a universal metronome, impartial and eternal, keeping pace whether or not matter existed to feel its passing. For nearly 2 centuries, this vision held. Physics was built upon Newton's stage, a clockwork universe moving across the theatre of absolute time. Motion was predictable, the heavens calculable. The cosmos was eternal, governed by immutable rhythm. Yet beneath the calm order of Newton's stage, cracks were waiting to open. In the late 19th and early 20th centuries, the cracks widened. Michelson and Morley searched for the ether, a medium through which light was thought to ripple, much like sound through air. If time was absolute, light should carry its speed through that universal stage, but their interferometer revealed no such drift. Light's velocity appeared constant, unshaken by motion. Then came Albert Einstein with the quiet upheaval of relativity. He saw what others had resisted, that time itself is not absolute, but bound to the motion of the observer. A second for one traveler may stretch into an eternity for another. In special relativity, time dilates. A moving clock slows compared to one at rest. A particle traveling near the speed of light lives longer, its decay delayed by its journey. Time is not universal, but elastic, stretched by velocity. In general relativity, Einstein went further. Time was not a neutral stage at all, but one of the players. Gravity was no longer an invisible force tugging at masses, but the curvature of space-time itself. Stars and planets bent the fabric of the cosmos, and time bent with it. Near a massive star, a second ticks more slowly than in interstellar emptiness. Near the abyss of a black hole, time nearly freezes for the distant observer. The ticking of the cosmic clock depends not on Newton's eternal rhythm, but on the landscape of space-time. For the first time, physics revealed that time itself is not fixed. It can be stretched, warped, twisted. It is not a universal march, but a malleable flow, braided into the geometry of existence. With Einstein's revolution, the universe itself seemed to gain a beginning. If space-time is curved, dynamic, and sensitive to mass and energy, then the cosmos is not eternal but evolving. In the early 20th century, astronomers turned telescopes skyward to test this vision. Vesto Melvin Slipher measured the light of galaxies and found a strange redshift, as though they were receding. Edwin Hubble expanded this view, discovering that nearly all galaxies were moving away. The farther they were, the faster their retreat. The universe was not static, but expanding. Extrapolated backward, this expansion implied an origin, a moment when space was not stretched but compressed, a singularity of unimaginable density and heat, the Big Bang. Time itself appeared to have begun there, a boundary before which before had no meaning, and if time had a beginning, then perhaps it must also have an end. This realization was a shock to the human imagination. The eternal heavens of Newton had been replaced with a finite history, a cosmos with a birth. Time was no longer a river without source. It was a river springing from a fountainhead. Philosophers struggled. Theologians debated. Scientists pressed further, armed with mathematics and observation. The cosmic microwave background, discovered by Penzias and Wilson in 1965, provided the echo of creation itself. Radiation stretched thin across space, a fossil of the early universe. With it came confirmation. Time as we know it began in a fiery origin. From the cyclical heavens of ancient civilizations through Newton's absolute stage to Einstein's pliable space-time, the idea of time had transformed. It was no longer a backdrop, but a participant, no longer eternal, but bounded. Yet beneath these triumphs, a deeper unease stirred. For if time could bend, slow, and perhaps even end, what did that mean for human perception of its flow? What if what feels like the steady unfolding of the present is only a local illusion, within a cosmos that already holds its beginning and its end, both written, both complete? Thus, the discovery phase did not end with answers, but with an unsettling horizon. Humanity had unmasked time as something more fragile than myth, more fluid than Newton, more finite than once imagined. The clock of the cosmos had been wound at the Big Bang, and one day it may wind down. The question left hanging in the silence: if time has a beginning and an end, then what, truly, is happening in between? The universe tells its story through a single direction. Stars burn and fade, glass shatters but never reassembles, memories reach backward but never forward. This is the arrow of time, the greater symmetry of existence. It seems so obvious, so undeniable, that it rarely invites suspicion. But for physics, the arrow of time has always been a paradox. The laws that govern atoms and planets, quantum waves and cosmic fields, they are, at their core, reversible. An equation describing a falling stone works equally well if its trajectory is reversed. The Schrödinger equation of quantum mechanics allows particles to unfold forward or backward in time without contradiction. Nothing in the mathematics forces time to flow in only one direction, and yet reality insists that it does. The past is remembered, the future is anticipated. Heat disperses, order decays, structures collapse. It was Ludwig Boltzmann, the Austrian physicist of the 19th century, who first offered an answer. Boltzmann peered into the hidden world of atoms, invisible in his time, but revealed through mathematics. He suggested that the disorder of a system, what he called entropy, measures the number of microscopic arrangements that correspond to its macroscopic appearance. A gas in a box, for example, might contain trillions of molecules. If they cluster together in one corner, that is a highly ordered, highly improbable state. If they disperse evenly throughout the box, that is disordered, but overwhelmingly more likely. Thus, time's arrow emerges from probability. Systems evolve from the improbable toward the probable, from order to disorder, not because the laws demand it, but because statistics do. Boltzmann's vision was both elegant and unsettling. It implied that the arrow of time is not fundamental, but accidental, not carved into the bedrock of the universe, but born from chance. In principle, the molecules of a cooled cup of tea could spontaneously reassemble their heat into one corner, boiling it again. Nothing in the laws forbids it. It is only vastly improbable, so improbable that it will not happen in the lifetime of the cosmos. The universe's direction, it seemed, is the mathematics of luck. This statistical vision raised disturbing questions. If time's arrow is only probability, then irreversibility is not real. Given enough time, everything could happen again. Henri Poincaré, the French mathematician, sharpened this paradox with his recurrence theorem. He showed that in a finite system, governed by deterministic laws, the arrangement of particles must, given infinite duration, return arbitrarily close to its starting point. A shuffled deck of cards, shuffled endlessly, must one day return to perfect order. A dispersed gas must someday gather again in its corner. Given eternity, the improbable becomes inevitable. So why does time feel irreversible? Why does the arrow point forward with such certainty if the equations of the cosmos are reversible? And more haunting still, if the universe truly recurs, then every moment has already happened, countless times before, and will happen again, countless times hence. Here lies the first great scientific shock. The realization that the arrow of time is not written into the universe's laws, but emerges only from initial conditions, from the unlikely order in which the cosmos began. The early universe, only moments after the Big Bang, was smooth, low in entropy, astonishingly ordered. Out of that fragile beginning, disorder was free to grow, driving stars to ignite, galaxies to form, planets to cool, and life to emerge. But this raises a question more profound than it answers. Why was the beginning so ordered? Why did the universe start in a state from which time could unfold at all? As the 20th century advanced, the shocks deepened. Einstein's relativity had already shattered Newton's stage of absolute time, replacing it with space-time, a fabric in which time and space are inseparably woven. Within this framework emerged the most disorienting idea of all, the block universe. In this model, the past, present, and future do not flow, but coexist. All events, from the birth of the first star to the last flicker of the cosmos, exist together in a four-dimensional structure, like pages of a book already written. The flow of time is not a river sweeping us forward, but an illusion born of perspective, the way a reader moves through a story already complete. To stand inside the block universe is to face a disquieting thought. The end of time is not waiting in the future. It already exists, as real as this moment, as real as the past. Humanity moves through space-time not as travelers of an unfolding reality, but as passengers along a pre-drawn map. This vision carries philosophical shockwaves. If the future is as real as the past, then what becomes of choice? If the last second of the universe already exists, frozen in space-time, then is the sense of becoming, of change, of flow, nothing more than the trick of consciousness, replaying slices of a cosmic monument. Some physicists resist the block universe, preferring a model where only the present is real and the future unwritten. Others embrace it, noting that relativity itself seems to favor eternalism, the idea that all of time exists equally. But whether the cosmos is a block or a flow, the fragility of time has been exposed. It is not absolute, as Newton once believed. It is not guaranteed, as experience suggests. It is a construct, statistical, relative, emergent. This fragility unsettles not only physics, but meaning itself. If time's arrow is born only from improbable beginnings, then its persistence is temporary. If recurrence is inevitable, then even death and loss are destined to repeat. And if the block universe is true, then the end of time is not ahead of us. It is already here, stitched into the fabric of reality, existing alongside this moment, unseen yet unavoidable. The scientific shock is not merely that time bends or slows or stretches. It is that time may not flow at all, that what feels most immediate, the rushing forward of the present, may be the deepest illusion of all. The hands of the cosmic clock move, but its gears may be still. Entropy ticks forward, but only because the universe began improbably smooth. Reversibility waits in the shadows, recurrence hides in infinity, and the end of time may already exist, watching in silence. The question grows darker. If the flow of time is an illusion, then what, exactly, is it that consciousness is experiencing? The search for time's essence could not remain in philosophy alone. Humanity turned its eyes to the heavens. building telescopes that extended vision far beyond the reach of flesh, and equations that penetrated deeper than imagination. What emerged was a strange portrait of time, measured, charted, mapped across cosmic history, yet always elusive, always slipping through the fingers of definition. In the early 20th century, light from distant galaxies revealed a story of motion and memory. The faint glow stretched toward the red end of the spectrum, a signal that these galaxies were receding. The farther they were, the faster they seemed to flee. This discovery, the redshift, transformed cosmology. It showed that the universe was not fixed, but expanding. Space itself was stretching, and with it, the very fabric of time. Extrapolated backward, this expansion led to a single origin, a moment 13.8 billion years ago, when the observable universe was compressed into extraordinary density and heat. The birth of space, the birth of time, the Big Bang. To measure the age of the universe was to measure the age of time itself. Telescopes became clocks, their lenses catching the light that had traveled across billions of years. Each photon a messenger from the past, each galaxy a bookmark in the chronology of space-time. And then, in 1965, a faint background glow was detected, not from stars, but from the universe itself. Arno Penzias and Robert Wilson, pointing a radio antenna toward the sky, stumbled upon a whisper, the cosmic microwave background. Radiation stretched thin by 13.8 billion years of expansion, the frozen afterglow of the first fire. It confirmed the timeline. Time since the Big Bang could now be measured. But here a paradox revealed itself. To say the universe is 13.8 billion years old is to assume a flow of time that might not truly exist. If all of history is already present in the block universe, then 13.8 billion years is not an unfolding, but a dimension, a length measured across space-time, no more flowing than the height of a mountain. If telescopes measure time on the largest scales, black holes reveal it at the most extreme. Around these collapsed giants, time itself bends to its breaking point. General relativity predicts that near the event horizon, the invisible boundary beyond which nothing can return, time slows drastically compared to the outside universe. To an astronaut hovering just above the horizon, a second would pass as years unfolded in the cosmos beyond. To a distant observer, the astronaut's clock would appear frozen, her descent into darkness endlessly delayed. Time, seen from afar, seems to halt at the threshold of a black hole. This paradox blurs the line between perception and reality. Is time truly stopping at the horizon, or is it only the distortion of perspective? For the falling traveler, time continues without interruption, rushing toward the singularity. For the observer outside, time stretches until it seems infinite. Here, relativity exposes its strangest truth. Time is not universal. It fractures, dependent on gravity, dependent on velocity, dependent on where one stands in the geometry of space-time. Black holes become laboratories of time, natural experiments carved into the universe. They suggest that the flow of moments is fragile, malleable, perhaps even dissolving in the singularity where the known laws of physics collapse. On the smallest scales, the mysteries deepen further. Quantum mechanics describes particles not as definite objects, but as wave functions, superpositions of all possible states, unfolding until measurement collapses them into certainty. But within these equations, time plays a curious role. The Schrödinger equation requires it, yet the system it governs does not explain its origin. Time is smuggled into the mathematics, not derived from it. Even stranger, certain quantum phenomena seem to operate outside ordinary time. Entangled particles react to each other's states instantly, across vast distances without delay. Experiments confirm this spooky action at a distance, yet no signal passes faster than light. Perhaps the entanglement exists in a framework where time as humans know it does not apply. At the level of quantum fields, where virtual particles flicker in and out of being, time seems less like a river and more like a bookkeeping device, a way of ordering events, not an entity in itself. This has led some physicists to wonder, is time fundamental at all? Or is it an emergent property, like temperature, real, but arising only from the behavior of deeper constituents? The rift between relativity and quantum mechanics has long been physics' greatest wound. Relativity treats space-time as a smooth continuum, warped by mass and energy. Quantum theory treats particles and forces as discrete, probabilistic events. Each reigns supreme in its own domain. But at the singularity of black holes and the first instant of the Big Bang, both break down. To reconcile them, scientists have sought to quantize space-time itself. Loop quantum gravity imagines that space and time are not continuous but granular, woven from indivisible loops of geometry. Just as matter is made of atoms, time may be composed of quanta, discrete moments, finite, countable. In this view, the smooth flow of time is an illusion born of scale, the way a movie appears fluid though built from still frames. String theory offers another vision. It proposes that particles are not points, but tiny vibrating strings, their harmonics giving rise to all matter and forces. In this framework, time may not be fundamental but emergent from the symphony of strings and higher dimensional shapes. Neither approach is proven. Each remains speculative, contested, incomplete, but both suggest that what humans perceive as time may be an approximation, a shadow of a deeper structure where before and after dissolve. Through telescopes, humanity has mapped the age of the cosmos. Through relativity, it has bent time around stars. Through quantum theory, it has questioned whether time exists at all. Yet at every step, time resists definition. It appears in equations, but without origin. It stretches and contracts, but offers no explanation for why it should move forward. It dissolves in black holes, re-emerges in probability, and perhaps vanishes entirely at the Planck scale, the unimaginably small frontier where physics has no map. The deeper science peers, the more fragile time becomes. Perhaps it is not a flow, but a scaffolding, not a river, but the illusion of one. In the silence between equations and stars, a question lingers. If time can bend, halt, recur, or dissolve, then what is the reality behind human experience of its passing? Are humans witnesses to a river of becoming, or are they only moving shadows across the surface of a frozen sea? The deeper science pressed into the fabric of time, the more fragile it appeared. At first, it bent, slowed by gravity, stretched by speed. Then, it fractured, a probability in the hands of quantum mechanics, a frozen monument in the block universe. But as cosmologists gazed farther, toward the fate of the cosmos itself, time grew darker still. Its flow seemed to carry not only moments, but the certainty of an ending. The universe, as observed today, is alive with energy. Stars burn hydrogen into helium, releasing light and heat. Black holes devour matter, their violent edges erupting in radiation. Galaxies spin, planets orbit, chemistry churns into biology. Yet every act of creation is also an act of consumption. Energy disperses, never lost but always diluted, spread thinner across the cosmos. This process is entropy on the grandest scale. Extrapolated forward, entropy points toward a chilling horizon, the heat death of the universe. In this scenario, all usable energy will eventually be spent. Stars will exhaust their fuel, collapsing into white dwarfs, neutron stars, and black holes. Galaxies will fade into darkness. Black holes themselves will evaporate through Hawking radiation, shrinking over inconceivably long timescales until even they vanish. What remains is a cosmos in perfect equilibrium, matter and energy evenly spread, no gradients left to drive motion, no structures left to sustain change. It is not a fiery apocalypse, but a silent one. In such a state, there is no difference between one moment and the next. Without change, time itself loses meaning. The arrow of time, born from entropy's increase, would finally dissolve into stillness. In this bleak horizon, the story of time does not climax. It simply fades into endless silence. Though the heat death is the prevailing vision, it is not the only one. Cosmology offers multiple endings, each shaped by the fate of expansion. If dark energy, the mysterious force accelerating the universe's growth, continues its relentless push, it could lead to the Big Rip. In this scenario, galaxies are torn apart as space itself expands faster than gravity can hold them together. Stars are ripped from their orbits, planets from their suns, atoms themselves stretched until they disintegrate. Time would not gently fade, but collapse in violence, shredded by the very fabric of space-time unraveling. Alternatively, if expansion slows and reverses, the universe could end in a big crunch. Galaxies would collapse back together, stars and black holes merging in catastrophic fire, all of space-time folding into a final singularity. In this end, time does not fade into silence, but implodes, rushing back to the density of the beginning. Between these extremes lies the Big Freeze, a universe that expands forever, thinning into darkness. Galaxies drift apart until their light can no longer reach one another. Stars die, black holes fade, and matter decays into subatomic fragments. This end mirrors heat death, though seen as a slow, cold unraveling rather than equilibrium. Each scenario speaks of time's fragility. Whether it rips apart, collapses inward, or freezes into stasis, time carries with it the shadow of conclusion. The driver of these cosmic destinies is dark energy, a force so strange that it reshaped physics upon its discovery. In the late 1990s, astronomers studying distant supernovae expected to find the universe slowing in its expansion. Gravity, they believed, must be pulling against outward motion. Instead, the supernovae revealed the opposite. Expansion was accelerating. Some unseen energy was stretching space-time itself, overpowering gravity on the largest scales. This discovery earned a Nobel Prize and an enduring mystery. Dark energy makes up nearly 70% of the universe, yet its nature is unknown. It may be a property of space-time itself, a constant vacuum energy that drives expansion forever, or it may evolve, changing strength across time, destined one day to weaken or to grow unstoppable. If dark energy grows stronger, the big rip awaits. If it weakens or reverses, a crunch may follow. If it remains constant, the universe drifts into freeze or heat death. The acceleration of expansion means that cosmic time is not just flowing, it is being stretched, distorted, forced toward one of these endings. Every galaxy drifting farther apart is a measure of time's fragility. Every red-shifted photon, a reminder that the universe is sliding towards silence. Yet, there is a darker possibility still. One that does not unfold over billions of years, but could arrive in an instant. Quantum field theory suggests that our universe may not be in its most stable state. It may be metastable, balanced in a false vacuum, rather than the true ground state of reality. If so, then a fluctuation could trigger vacuum decay. A bubble of true vacuum could appear somewhere in space, expanding at the speed of light, rewriting the laws of physics as it consumed everything. Matter, energy, forces, even the fabric of space-time itself, all obliterated or transformed beyond recognition. In this scenario, time would not fade or collapse. It would end entirely, instantly. No warning, no survival, no memory. The end of time itself, erasing even the concept of after. What makes this vision especially haunting is its inevitability. If the universe is metastable, such decay is not a question of if, but when. It could happen billions of years hence, or it could already have begun, its bubble rushing toward us, undetectable until the instant it arrives. Here lies the deepest terror of time, not only that it ends, but that it may already have ended. If the block universe is correct, then the end of time already coexists with the present, woven into space-time like a final page already written. If false vacuum decay is inevitable, then perhaps it has already occurred elsewhere, and all that is perceived now is the echo of a doomed timeline. If consciousness itself is bound to the illusions of flow, then humanity may already be replaying the last patterns of a static cosmos, like neurons flickering in the instant after death. The universe may already be over, and yet perception continues, watching the fading shadow of motion, as though time itself cannot bear to reveal its own absence. The investigation into time has thus escalated from paradox to dread. What began as cycles of the stars became Newton's stage, then Einstein's fabric, then Boltzmann's probability. Now, at the edge of modern cosmology, it is something even more unsettling, a fragile thread stretched toward endings that dissolve meaning itself. Heat death, rip, crunch, freeze, decay, each possibility more alien, more terrifying than the last. And yet in all of them, one truth remains constant. Time is not eternal. Its story has boundaries. Its horizon grows darker. The hands of the cosmic clock do not tick toward infinity. They tick toward silence. The question remains, if time can end in so many ways, then what is it truly that is experienced in its flow? The investigations of physics have carried humanity from the stars to the subatomic, from Newton's stage to Einstein's fabric, from entropy's arrow to black holes where clocks falter. But in the end, no experiment, no equation, no telescope has answered the simplest of questions. What is time? And so, in the shadow of evidence, speculation takes shape. Theories arise not from fantasy, but from the cracks between known truths. Each offers a different vision of time, and each whispers the same haunting suggestion. Perhaps the flow of time has already ended. Perhaps it never flowed at all. In the late 20th century, while studying black holes, physicists uncovered a startling paradox. Stephen Hawking's work on radiation implied that black holes could evaporate, yet general relativity said nothing, not even information, could escape. To lose information, however, would violate the core laws of quantum mechanics. The resolution came in an idea as strange as it was profound, the holographic principle. Proposed by Gerard 't Hooft and Leonard Susskind, it suggests that the universe's deepest description is not in the volume of space, but on its boundary. Reality, in this view, is like a hologram. The three-dimensional world emerges from information encoded on a distant two-dimensional surface. If the holographic principle is true, then time itself may not be fundamental. It may be part of the emergent illusion projected into the bulk of reality. The true universe may be timeless, its equations written in terms of static correlations, while what is perceived as time is only the unfolding of information across that hidden surface. In such a picture, the end of time would not be an event. It would be the recognition that the flow was never more than a projection, a story told by the boundaries of the cosmos. For decades, British physicist Julian Barbour has argued that time does not exist. His radical view is not metaphor, but literal. Barbour describes the universe as a vast collection of possible nows, complete configurations of the cosmos, each timeless, each existing in its own right. What humans perceive as the flow of time is simply the movement of consciousness through these nows, like a traveller passing across a landscape. In his Platonia, as he calls it, there is no true past, no genuine future. There are only nows, existing together, without order. Memory is not proof of time's passage, but a structure embedded in certain nows that give the illusion of sequence. If this is so, then time may already have ended because it never began. The universe is not evolving, but simply is, a timeless mosaic. The flow experienced is a projection of perspective, not a property of the cosmos. This vision is both liberating and terrifying, for it means that the last now, the final possible configuration of the universe, already exists alongside the first, and alongside this moment too. The machinery of becoming is an illusion. The world is a collection of still frames mistaken for motion. Italian physicist Carlo Rovelli offers another path. In his theory of relational quantum mechanics, time is not fundamental, but emergent from relationships. Rovelli argues that nothing exists in isolation. Properties only appear in relation to something else. Time, in this view, is no different. It arises not as an independent entity, but from the way systems interact. A pendulum swings relative to the Earth's gravity. A particle decays relative to its surroundings. The universe keeps no master clock. Instead, countless local processes create the illusion of a shared flow. In Rovelli's thermal time hypothesis, the arrow of time arises from the statistical state of the universe. The direction felt is a consequence of entropy, not a fundamental law. If so, then the end of time may simply mean the loss of interactions that sustain the illusion. As entropy saturates, as energy spreads evenly, as structure dissolves, time itself could dissolve with it, not because it stops flowing, but because it was never more than the shadow of relations. Behind these physical theories lies an older philosophical battle: eternalism versus presentism. Eternalism, favored by many physicists, aligns with the block universe. All times exist equally, past, present, and future, woven together into a static four-dimensional whole. In this vision, time has already ended in the sense that every event, including the final one, is as real as now. The universe does not move, observers do. Presentism resists this, claiming only the present is real. The past is gone, the future unreal. In presentism, time flows genuinely forward, and endings are true boundaries, not already existent pages. Each stance carries deep consequences. Eternalism erases free will, painting life as the reading of a story already finished. Presentism preserves openness, but struggles against relativity, which shows that simultaneity is relative and no universal now can be defined. Between them lies the unsettling realization: if eternalism is correct, then time's end is already written. If presentism is correct, then the end approaches inexorably. Neither leaves escape. Beyond physics, speculation extends to the digital. The simulation hypothesis asks whether reality itself is computation. If so, then time is not an independent flow, but a sequence of updates in a program. In this framework, the end of time could arrive not through cosmic physics, but through computation ceasing. If the higher-level machine stops, the simulation freezes. Inside, consciousness may still experience residual patterns, like circuits echoing after power loss, like the afterimage of light on closed eyes. This view raises a chilling speculation. What if the simulation has already been halted, but awareness drifts on? Inertia of mind replaying stored states while no true time elapses outside? Like a video paused mid-frame, reality could already be frozen while experience continues inside, mistaking the loop for motion. Across holograms, nows, relations, philosophies, and simulations, a singular possibility emerges, that the flow of time is not fundamental but experiential. Perception itself may be inertia. Consciousness could drift through static states, mistaking their arrangement for duration. The river may be imagined, the current only the mind stitching stillness into story. If so, then the end of time may already lie behind, or beside, or nowhere at all. The universe may be over, yet still seen. The cosmic clock may have stopped, yet its hands continue to move in memory. This possibility does not end with equations, but with existential dread, that what is lived as becoming, as unfolding, as destiny, may be only the ghost of a machine already silent. Speculation is not proof, yet it is the horizon of knowledge. Physicists and philosophers, staring into the silence of equations, have dared to ask, if time is fragile, if it can bend, halt, dissolve, or never exist, then what does it mean to live within it? The answers are many, but each carries the same chilling resonance. Time may not be a river, but a projection. Not a flow, but a mosaic. Not an entity, but a relation. Not eternal, but already complete. And in all of them, the end is not waiting in the future. It is here, always, already. The question remains, if time's flow is only illusion, then what is it that consciousness moves through? And if the story is already finished, then why does the echo of its telling still linger? Theories of time stretch across philosophy and mathematics, across speculation and paradox. But physics does not rest on speculation alone. It builds instruments, colossal machines, delicate detectors, eyes that pierce the cosmos, all to search for the hidden pulse of reality. If time has secrets, science seeks them in the smallest particles, the largest galaxies, and the faintest echoes of creation. Yet the search carries its own irony. All experiments must unfold within time, like shadows in a cage. Humanity cannot step outside the flow it questions. It can only watch how matter and light betray its patterns. At the heart of modern physics lies a principle. The laws of nature are symmetrical. If one flips space, reverses charge, or runs time backward, the equations should remain valid. Yet in practice, cracks have been found. In the 1960s, experiments with kaons, strange particles born in accelerators, revealed violations of time symmetry. The behavior of matter and antimatter was not perfectly mirrored. Decay processes favored one direction of time ever so slightly. This tiny imbalance suggested that the arrow of time may be written into the quantum world itself. Today, physicists continue this search in particle accelerators such as CERN's Large Hadron Collider. They probe rare decays of B mesons, scanning for traces of CP violation, a symmetry between matter and antimatter. The hope is to uncover why the universe contains matter at all, rather than annihilating itself in perfect symmetry at the dawn of time. Here lies a profound connection. The very existence of galaxies, stars, and life may be the result of subtle fractures in time's symmetry, a universe that is not perfectly reversible, but tilted ever so slightly toward the arrow of becoming. If any particle holds clues to time's secrets, it may be the neutrino, the ghost of the cosmos. Nearly massless, nearly invisible, trillions pass through every human each second, unnoticed. Neutrinos shift identities as they travel, oscillating between flavors. These oscillations may carry the fingerprints of time's asymmetry. If neutrinos behave differently than their antimatter twins, antineutrinos, it could help explain why matter dominates the cosmos. Experiments such as Japan's T2K, the United States Dune Project, and Europe's IceCube Observatory buried in Antarctic ice watch these elusive messengers. They chase tiny imbalances that could reveal how the early universe escaped symmetry and birthed the arrow of time. Each detected neutrino is a whisper from the heart of stars, from cosmic rays, from the first seconds after the Big Bang. Together, they may reveal whether time itself tilts slightly in favor of matter, and thus in favor of existence. While particle physicists chase time's arrow in collisions, quantum engineers test it in computation. Quantum computers, built from fragile qubits entangled in superposition, can simulate processes that mimic the reversal of time. In 2019, researchers at the Moscow Institute of Physics and Technology, working with IBM's quantum machines, demonstrated an experiment where the state of a quantum system appeared to rewind, evolving backward to a prior configuration. This was not a true reversal of time, but a controlled manipulation of quantum states, exploiting the reversibility of the Schrödinger equation. Still, it revealed that at the quantum scale, time may not be rigid. Processes can, in principle, unfold both ways, their direction determined only by initial conditions and probability. Quantum computers thus become laboratories not only for computation, but for metaphysics. They test whether time's flow is fundamental, or if the laws beneath it are indifferent, leaving the arrow to emerge only in the macroscopic world of entropy and memory. While colliders and qubits study time in the laboratory, telescopes stretch their gaze outward into the cosmic past. Launched in 2021, the James Webb Space Telescope is the most powerful eye ever opened to the heavens. With mirrors of gold and detectors chilled near absolute zero, it peers across 13.5 billion years, almost to the dawn of time itself. Webb does not see stars as they are, but as they were. Each photon it captures has traveled for billions of years, a memory of the early universe. By studying the first galaxies, the faint structures of rionization, and the patterns of the cosmic infrared glow, Webb helps reconstruct the conditions of time's earliest moments. It may test inflation, the brief, exponential expansion that stretched space-time itself in the first fraction of a second. Inflation, if true, shaped not only the size and structure of the cosmos, but the conditions from which time's arrow emerged. To look deeper into space is to look deeper into time, until one approaches the horizon where time itself was born. Webb's mission is not only astronomical but existential, to glimpse how time began, and thus how it might one day end. Einstein's relativity predicted that when massive bodies collide, they send ripples through space-time, gravitational waves. For a century, these waves remained undetected, until 2015, when the LIGO Observatory first recorded the tremor of two black holes merging. Gravitational waves are not just distortions of space, they are oscillations of time itself. As the wave passes, the rhythm of clocks changes, the tick of seconds stretches and compresses. Detectors like LIGO in the United States and Virgo in Italy now listen constantly to this faint music of space-time. They have revealed black hole mergers, neutron-star collisions, and perhaps, in the future, echoes from the earliest universe. Each detection is more than an astrophysical event. It is a direct measurement of time's geometry, vibrating. It confirms that time is not an abstract stage, but a material fabric, elastic, alive with motion. Future missions such as LISA, a space-based gravitational wave observatory, aim to listen even deeper. They may capture signals from cosmic strings, from inflation, from the first instance of creation. In their oscillations may lie answers to whether time has an origin woven into quantum gravity, or whether it is an emergent shadow of deeper laws. The search does not end with today's instruments. The coming decades promise new observatories and colliders, each probing the edges of time's mystery. The Future Circular Collider in Europe may explore energies far beyond today's accelerators, seeking traces of physics that shape the arrow of time. The Square Kilometre Array, the largest radio telescope ever built, will map the cosmic web across billions of light-years, charting how time sculpted galaxies. NASA's future probes may measure the cosmic microwave background with unprecedented precision, testing whether inflation left imprints in the polarization of ancient light. Each mission is not only astronomy or physics, but an inquiry into time itself. They ask, is time fundamental, or does it emerge from information? Is it continuous, or quantized? Does it flow, or is the flow illusion? And yet, for all these tools, a humbling truth remains. Science cannot step outside time to observe it directly. Every experiment unfolds in its grip. Every equation ticks with its rhythm. Every measurement assumes its existence. Like prisoners studying shadows on a wall, humanity watches time's effects, but never touches its essence. Telescopes see its past, colliders test its asymmetries, quantum machines toy with its reversibility, but the thing itself, time as reality or illusion, remains hidden. Perhaps the cage cannot be broken. Perhaps the very act of asking ensures the answer is unreachable. Still, the search continues, for in every shadow, in every ripple, in every whisper of ancient light, there may yet lie a clue. The tools grow sharper, the eyes clearer, the machines more powerful, but the mystery remains untouched at its core. Time, whether flowing or frozen, eternal or ended, reveals only fragments, and so the question grows heavier. If science cannot escape time's cage, then will its true nature always remain beyond reach? Time has always felt like a river. Its current carries life forward, sweeping moments away into memory, pushing the unknown toward the horizon of tomorrow. Humanity builds its calendars, its histories, its futures upon this flowing stream. But what if the river does not move? What if all that is experienced as current is only the illusion of drift, while beneath, the water is still? Perhaps humanity does not stand upon the shore of a rushing torrent, but in the middle of a silent lake, mistaking ripples in perception for motion through eternity. Memory feels like proof that time flows. Events are recalled in order, like footprints left in the sand. Yet neuroscience shows that memory is not a recording, but a reconstruction. The brain assembling fragments into a story that feels coherent. If memory is the architecture of consciousness, then its order may not be evidence of a flowing river, but only the scaffolding of perception. A photograph can be arranged into sequence. A mind can be built to experience one moment after another, even if all moments exist at once. The past may not be gone. The future may not be unwritten. It may be that memory creates the illusion of passage, and anticipation creates the illusion of destination. Between them, a species feels time's river while standing in a frozen sea. Of all known creatures, humanity alone asks whether time is real. A bird migrates, a star ages, an atom decays. None question the flow they inhabit. Only this species looks upward and wonders if tomorrow already exists, if destiny is already concluded. There is a loneliness in this questioning, the solitude of intelligence confronting its own limits. To ask if time is real is to ask if life itself is real, or only the unfolding of a script written beyond comprehension. The question cuts into the core of existence. Is there a future waiting to be shaped, or only one already complete? If the block universe is true, then every choice, every path, every outcome already stands inscribed in space-time. Free will becomes a shadow, the sensation of decision written into the script but never truly open. The actor walks the stage, believing the play is unfolding, yet the script is already finished. The audience is every observer in every moment, each convinced of improvisation, yet each bound by inevitability. If presentism is true, if only the now is real, then freedom exists but is chained to the relentless advance of an unknown future. The present burns, then vanishes. The arrow cannot be stopped. In both visions, free will is fragile. Either it is an illusion within eternalism, or a desperate spark burning only in the instant of presentism, extinguished as soon as it appears. To live within time's illusion may mean that choice itself is illusion, the self only a witness to a story already finished. What then becomes of meaning if time is illusion? If time has already ended, yet consciousness continues, then meaning may not lie in outcomes or futures at all. It may exist only in presence, in the stillness of each moment, regardless of sequence. Perhaps meaning is not in the unfolding of time, but in the awareness of it. A sunset holds beauty not because it leads to night, but because of its being. A memory is cherished not because it is past, but because it exists at all, engraved in perception. If all nows coexist, then meaning is eternal, not because time flows, but because no moment is ever lost. Every smile, every sorrow, every life remains forever in the frozen monument of space-time, indelible, untouchable. Imagine a theatre after the performance has ended. The stage is empty, the actors gone, yet the set still stands, and the echo of voices lingers. The light fades slowly from the rafters, and the dust holds the shape of movement long past. Perhaps humanity lives in such a theatre, the play of time already concluded, the ending already written, the actors already departed, yet perception remains, still watching, still feeling, still mistaking echoes for reality. If time's machinery has stopped, consciousness may yet drift in its inertia, the afterimage of existence, the echo of the play. The greatest discoveries of physics have not solved time, but shattered its certainty. Entropy suggests that the arrow is probability, not law. Relativity insists that time is relative, not universal. Quantum mechanics hints that it is emergent, not fundamental. Cosmology warns that it will end, not endure. And so the most haunting possibility remains. What is lived as the flow of time may already be over. Humanity may be standing in the ruins of a motionless cosmos, still perceiving, still remembering, still anticipating, even as nothing truly moves. Perhaps the river never flowed. Perhaps the stage is silent, yet the echo continues. Perhaps all that is experienced as becoming is already concluded. The final question lingers in silence, without answer, without resolution. What if time's story is already over, and all that is heard now is its fading silence?